Resisted motion. So this is going back to that idea when we looked at forces earlier. Resistance is always in the opposite direction to your motion. Basically, that's Newton's third law we're playing with. There's pretty much three cases. If all we're considering is straight line motion, is horizontal motion or vertical motion. But I say three cases because when we have vertical motion, we might be going up, we might be going down. So three cases. So let's look at the first one where we're just going in a horizontal line. So I'm going to define positive to be going to the right. So my resultant vector's there. So the only force that we would have on this problem is resistance. So if I'm travelling to the right, there'd be resistance to the left. So I'd end up with some sort of equation like this. Mx double dot will equal minus whatever function they've given us for resistance. I'd divide by m and then just integrate whatever that expression is. So that would be horizontal. If we were going up, and I always define the resultant to be the direction I'm travelling. So my resultant's going up. So the forces into play here, well, I'm going to have the force due to gravity, but also we'll have resistance as well. So this time I'd get something that looks like this. Minus mg minus whatever the resistance happens to be. Once again, divide through by m, and then play with that equation. It doesn't change the physics of the situation. If you want to find things like the greatest height, it's still going to happen when velocity equals zero. That hasn't magically changed because we've got resistance. I mean, those sort of ideas are still true. Downwards motion. So now my resultant is going to be going down. That's how I'm going to define it. So I'll have force due to gravity going down, but now resistance will be going up. So this time I'd get an expression that looks something like that. mg will now be positive. Resistance will still be negative. Divide through by m. There's our equation. Downward motion, we also have this other thing called terminal velocity. Terminal velocity, also known as limiting velocity. Essentially, it happens when acceleration is equal to zero. We'll start off with last year's HSC question. What did they give us the first year of this new course? So 50 kilo box, initially at rest. It's being pulled along the ground with a force of 200 newtons at an angle of 30 degrees to the horizontal. The box has a resistive force, which I would assume would be friction if we're on a surface, something like that probably, of 0.3 R newtons. Well, that makes sense because R they've defined to be the normal force. And remember how I said friction is always some constant times the normal force. So yeah, so that probably is friction we're looking at there. Take the acceleration to be 10, makes the maths a little bit easier. By resolving the forces vertically, show that R, I wish they hadn't have used R because I want to say R is resistance, but that's not in this case. R is the normal force. Why didn't they use N? Okay, so there's the diagram that they gave us. So we want vertical forces. I've got one that's at an angle, so I'm going to have to break that into components. I'm only interested in the vertical force though. So I'm going to draw up a little force diagram. Vertical forces. I've got 50 G going down, the force due to gravity. I've got the normal force going up, which we're calling R. And we have the component of that force at an angle. That would be 200 sine 30. Okay, now what I know here is that all the vertical forces are going to sum to be zero. I mean, this box isn't magically jumping off the ground. It's staying stationary vertically, as far as we're concerned. I could have said resultant force all adds up to be zero, however I say it. But basically, all those forces will sum to give zero. And that will allow me to find R. So substituting in for G being 10, we get a nice R is 400. Show the net force horizontally is approximately 53.2 newtons. Now we want to look at the horizontal forces. So I'm going to say the resultant force is going to the right. Component of that force that's at an angle, that'll be 200 cos 30. We also have that resistive force of 0.3 R, but that's all we've got horizontally. So my resultant force is 200 cos 30 minus 0.3 R. We, of course, have worked out what R is already. Oh, by the way, net force is, of course, the same thing as resultant force. So it's now just a matter, well, my resultant force is the net force horizontally. That's what I'm looking for. And again, it's just a matter of subbing in what we know. R is 400, cos 30 is root 3 on 2. They've said show 53.2, so we'll get an approximation there, and sure enough, that is 53.2 approximately. Find the velocity of the box after the first 3 seconds. Remember, we've just shown that the resultant force is 53.2. So dV to T would be 53.2 divided by 50, the mass. So 133 on 125. So the integral from 0 to V, right, initially it was at rest, will equal 133 on 125, the integral of the T from 0 to 3, and we're trying to find V. Here's the interesting thing about that one. Did I really need to use integration? Because we're moving with a constant acceleration here. So, you know that classic speed equals distance over time? Well, when you're talking about constant acceleration, you sort of can take that formula up another layer. So speed equals distance over time, well, acceleration will equal velocity over time. So I could have just said, oh, well, velocity is acceleration times time. And if you have a look at that second last line, that's essentially what I've got there. Acceleration times the time. That, of course, is only true if we've got constant acceleration. If we didn't have constant acceleration, we couldn't do that. Second example. Particle projected vertically up, velocity of u, in a resisting medium. Okay, assuming that the retardation due to this resistance is kV squared, find expressions for the greatest height and the time taken to reach that height. Okay, so we're going up. I'll define my resultant force to be going up. We have force due to gravity going down. We'll have that resistive force of kV squared going down. We know that when x equals 0, v is equal to u. That's pretty much it, isn't it? So, okay, resultant force will be minus mg minus kv squared. Divide through by the mass. Now, it's going to make it easier to have that all as one fraction, so we're going to separate out those variables. So v to v dx, because I'm trying to link velocity and displacement together here for the first part, because I want to find the greatest height reached. Flip it upside down, dx to v is mv or minus mg minus kv squared. Separate our variables. We have integral of dx is, well, I've factorised out the mass there. In fact, I've factorised out the negative as well to make life a bit easier. We've got v to v on mg plus kv squared, which is a log situation, but I'd actually like 2 kV on the top there. So I've just balanced it out. I now have m over 2k over the front. So that'll be m on 2k, the log of mg plus kv squared, sub in u, sub in 0, and we have this lovely expression. M on 2k log 1 plus ku squared on mg. That was the first part. They also want us to find the time taken. All right, time taken, back to acceleration, but this time I'm going to use, dv to t, because I want to link velocity and time together this time. But same idea now that I've got my variables, separate them, but this time the integration becomes an inverse tan. Oh, look at that lovely thing. M on k, square root of k on mg, inverse tan of the square root of k on mg v, sub in u, sub in 0. Well, at least that bit's nice. Inverse tan of 0 is 0. And what a beautiful expression. T ends up being the square root of m on kg. No, that's not kilograms. Inverse tan of the square root of k on mg u. This one. Let's do one where we're dropping the object. We want the velocity after time t for this one. So let's say, okay, we're dropping it. So I'm going to make the resultant force going down. They told me the mass was 5, so I'll call it 5 times the acceleration. And we have a resistive force. Oh no, sorry, that's gravity I've put in, isn't it? Mass times g. So we have the force due to gravity, 5g. The resistive force is Okay, read it carefully. Air resistance is proportional to speed. The constant of proportional being 1/8. So essentially they're just saying it's an 8th v. Why they couldn't just say that, I don't know. Now we're trying to find velocity after time t. So link v and t together. I'll use d t, separate out the variables. And again, we have a beautiful expression. 40 log 40g on 40g minus, oh yes. That's t in terms of v. We'll want v in terms of t. So now let's make v the subject. T over 40 is log, exponentialize both sides. I'll turn them upside down so it now becomes e to the minus t on 40. There we go. V equals 40g, 1 minus e to the minus t on 40. Terminal velocity. I know terminal velocity will happen when the acceleration is equal to 0. Solving that, I get v equals 40g. That's one way you could do it. But we also have a velocity time equation. And we said terminal velocity is limiting velocity. So I could look at the velocity equation and go, well, e to the minus t on 40 as t approaches infinity, well that bit's going to be 0, so I'm just left with 40g. So that's another way we could find our terminal velocity. How far has it fallen after time t? So back to dx to t. That's what we're going to integrate this time. So integral of dx is 40g, integral 1 minus e to the minus t on 40. We want to know how far it's fallen after time t. Well, we're dropping it from rest, so I know when t equals 0, displacement is 0. That's where we're starting. So x equals, integrating that, we get t plus 40e to the minus t on 40. Subbing in. Oh my goodness, we're getting some great expressions now. All right, last example. Question 16 in last year's HSC paper, which was the last question of the paper, of course. Well, 16A, there was a B, you know. Was there a part C as well? But anyway, we have this pulley question. We got a 2m kilogram and a 4m kilogram attached by a light string. Two masses are at rest before being released. Force due to air resistance on each mass has magnitude kV. K is a positive constant. Show that d to t is this expression. I don't know why they wrote it as gm instead of mg, but they did. Anyway, gm minus kv over 3m. Maybe it's alphabetical order. So let's investigate. We've got two different objects here. So let's have a look at both of them. On the left-hand side, our mass, the force due to gravity would be 2 mg. The resistance, they said, was kV. But don't forget about the force, tension. And that we're going to need to link the two masses together. So 2 mx double dot, that would be our resultant force, will be tension, because it will end up going up. Now, once you let that pulley go, logically you would think that 4m mass will pull and come down. Forces on the right mass then. Force due to gravity will be 4 mg. Its resistance will be kV, because it's going to be falling. But tension's there as well. So that one's 4 mx double dot is 4 mg minus t minus kV. All right. So if on the left-hand side, I'll make t the subject of the formula, and then I'll substitute that into the right-hand side. Now, we just need to tidy that up. We get 6 mx double dot is 2 mg minus 2 kV, and so there's the expression that they were looking for. The acceleration is mg minus kV over 3m. Given that velocity is less than gm on k, show that when t is 3m on 2 log 2, the velocity of the larger mass is gm on 2k. Okay, we've just worked out d to t is that expression. So, separate out the variables. We're releasing it from rest, so t equals 0, velocity is 0. We want to know what is the velocity when t is 3m on k log 2. Right. Well, the right-hand side is just a 0 to 3m on k log 2 of the t. So we'll just end up with 3m on k log 2. Left-hand side, let's work that one out. Pull out some constants. mg, what's this going to be? It's going to be a log, isn't it? So that's why I want minus k on the top. So I've got the coefficient of v on the top. So log of mg minus kv, sub in the v and the 0. I've put it all in at once. Is log 2. Now, They've told me velocity is less than gm on k. Well, that's telling me then that expression has to be positive. So when it comes to absolute value, it will just be that expression. mg on mg minus kv is 2, and we end up with the required result. V is mg on 2k. 6D, 6E.